covering redshift and blue shift, that is Doppler effect and the electromagnetic radiation, which you have already understood, right? We
Yes,
have why the universe is expanding and then Hubble's law.
yes,
Okay, so the universe is expanding. Obviously, we are aware that in 1920, Einstein had developed a theory which is known as general theory of relativity, right?
yes, ma'am.
And Einstein and Friedman were developing their theories. Okay, whereas there were many scientists like Edwin Hubble was there, then Westo Slipher was there. They were taking the measurement criteria. Okay, so Slipher was measuring the line spectrum from the distant galaxies, and the Hubble was measuring how far away they are. Okay, so they all are working in a group, but they all were working on different perspectives, right?
Yes, ma'am.
What did I told you? That the Slipher was the scientist who was measuring the line spectra. Yesterday we had seen a spectrum.
Yes,
Check
yes,
here, this one, spectrums.
yes,
Okay, so he was measuring the line spectrums, and Hubble was measuring from that how far away a particular orbit or a particular planet is. Done.
yes, ma'am.
So Slipher has discovered that the spectral lines from all the galaxies were shifted towards the red end, and this was due to the Doppler shift, obviously. Okay. What does the Slipher had conveyed? That he discovered that all the spectral lines that is been coming from the galaxies, they were moving towards the red end. So red end means obviously it's a very high wavelength. It is, that means they are coming from a very far off places, making sense. And
Yes,
if they are coming from a very nearby objects which are moving towards us, then they will be giving you the blue shift. Correct or not? Because
yes,
blue
ma'am.
shift is for nearby objects. Their blue wave is carrying a shorter wavelength. Shorter wavelength means they are covering less distances, right?
Yes, ma'am.
Okay, so the concept is very clear that if I am drawing, okay, let me draw it with the colors only I am having. So red shift is basically long wavelengths. Okay, their wavelength is very, very long. Okay,
Yes,
but if I take the blue color, then their wavelength is very, very small.
ma'am.
Okay, so basically they are traveling less distances. So if they
And
are
higher
coming
frequency.
from, sorry,
And they have higher frequency, blue shift.
yeah, exactly. So here these galaxies are obviously going away from our planet. Okay, suppose this is our planet Earth. Okay, so that means what? That these are going away from us and these are coming towards us. Making sense?
Yes, ma'am.
Okay, because in the Doppler shift, what did we observe? That if anything is coming towards us, that we had observed here only. Let me show you the picture. If the wavelength gets shrink, correct? If it is
Yes,
steady, then it is okay. But if it is coming towards us, so see the blue color is observed. Why? Because it is getting shrinken. So if it is getting shrinken, so the wavelength decreases, hence it is nothing but blue color. And if it is going away, then obviously the wavelength, here you can see that the wavelength distance is increasing, right? So the increasing wavelength is of what? Red color. So if I am observing red shift, that means the object is going away from me. If I am observing blue color, because the wavelength is getting shorter and shorter and shorter, due to the Doppler effect, I can convey that this is the blue shift happening. Correct or not?
yes, ma'am.
Okay. So hence all galaxies coming, the shift that has been observed by Slipher is red shift. That means what? They are going away. Hence the universe is expanding, obviously,
Yes, ma'am.
because they are moving away from the earth. Okay, these are moving away from earth, these are coming towards earth, but we have obtained only red color from all the galaxies. Okay, then Hubble had calculated over here the velocities of the galaxy. Okay, what did he say? That v over c is nothing but lambda, v over c equals to lambda, correct?
Yes, ma'am.
Okay. Over change in lambda over original lambda. Original lambda is obviously of electromagnetic wave. That is nothing but he had given a increase in the parameter of the how the wavelength is changing when it is coming towards and it is going away with respect to the original wavelength. Making sense? So here, these patterns, let me tell you what are they actually give up. So the velocities of the galaxies which are going away and from us, that is from Earth, is given by this formula. Check. V over C equals to del lambda. Okay. Del lambda
ma'am.
over lambda of EM. That is, I told you the ratio of change in wavelength over original wavelength. Okay. V is what? Recessional velocity. Recessional velocity means which is going away from us. Okay. The speed of light. Lambda is the change in wavelength. As I told you, lambda is the original wavelength originally emitted from the galaxy, and Z is the fractional increase in the Z parameter. Okay.
Yes, ma'am.
Okay. So Z has no unit because obviously del lambda over lambda will be meter over meter and they will cancel out each other. Similarly, V over C is also meter per second, they will cancel each other. Hence, Z parameter is the ratio of the velocities with which it is going away and the velocity of the EM wave. The, that is also equal to change in the wavelength which it is going away and the original wavelength. So these ratios are actually giving us the parameter of Z, which is what? Fractional increase. Okay, understood or not?
Yes, ma'am.
Okay, any doubts till here?
No, ma'am. No, ma'am.
Okay, great. Now after this we are having Hubble's law. So basically in 1929, Hubble has published a discovery that appeared the linear relationship between what? The recessional velocity. Recessional velocity means what? With which it is moving away from us. Okay. And the distance to the galaxy. Okay. And what does he found? That it is giving a linear relationship. Okay. Let me show you that thing also. Check. So recessional velocity versus distance. So these are the galaxies and they are going away. Check. Okay. As the distance is increasing, their velocity is also increasing. Making sense? So hence here
Yes,
we
ma'am.
can convey that V is directly proportional to D,
Yes, ma'am.
which he converted into proportionality constant, that is Hubble constant equals to D. So H naught here is the Hubble's constant and its value is fixed, that is given by him, and that is the gradient of this line, which is nothing but 72 kilometer per second mega parsec. Okay, making sense?
Yes, ma'am.
Okay, any doubts?
No, ma'am.
Okay, so this is the rate of measurement of with which the universe is expanding. Making sense?
Yes, ma'am.
Okay, so this was it, and after this we are having unit D, that is fields. Let's start with D1, and that is your gravitational fields. Okay, so in this chapter, what we have to do the study of? We have to do the study of gravitational force and field. So in this, we have the very first topic, and that is gravitational force and field. So just pay attention when we are doing the study of gravitational force and field. Basically, we have here the Newton's law of gravitation, and that is the universal law. Okay. So what does the Newton's universal law of gravitation suggests? So it basically suggests us that in this universe, if we have any two masses, any two, okay, then the line which is joining the centers of the two mass, you have to draw the centers only, okay, which is carrying a distance r. So here the force with which they are attracting each other, okay, the force with which they are attracting each other is directly proportional to the product of these two masses and inversely proportional to the square of the distance between them. Done? Hence, we get it as combinedly m1 m2 over r square. So if I convert it into gravitational constant, then it will be m1 m2 over r square. So here the value of g is obviously fixed, and that is the universal gravitational constant, and it is 6.67 into 10 raised to minus 11. How do we got the SI unit for g? So g is given as f into r square over m1 into m2. So f is Newton, r square is what? Obviously the meter square per kg square. Done? So this is the value of capital G. Understood? Now there are
Yes.
some properties of this particular law. The very first property is this force is always attractive in nature. Second thing, this force is always applied from the centers of the two masses. Okay. Third thing is this force is only and only significant for the heavy bodies. Okay. Fourth thing is this is not repulsive. Okay. This is never ever be repulsive in nature. And other thing that you can say is as the distance increases, the force decreases. Okay.
Yes, ma'am.
Okay, done. So now after this we have another thing, and that is this. Suppose here is the sphere, then at the center, from the center you will see the gravitational force has been applied at a normal line of the mass. Always the normal line of the mass, wherever the mass is, okay, it is applied because it is always coming from the center. So inside the sphere it does not have any gravitational force, but the maximum gravitational force is found over here. Okay, done.
Yes.
Okay, so now after this we are having gravitational field. Now what does this convey is that around a sphere, the region in which its gravitational pull is experienced by any mass, okay, that is the gravitational field strength is defined as force experienced by per unit mass. Making sense?
Yes, ma'am.
Okay, so this is particularly applied for only masses, and the SI unit is Newton per kg. Done? Okay?
Yes, ma'am.
Okay. So this is the formula for this. Let's move ahead. Do you want to discuss anything? I don't think it's very tough topic.
No, ma'am.
Okay. Now let's discuss about gravitational field around a spherical object. So just pay attention. The gravitational field or the force experienced by a mass, okay, is obviously given by this thing, capital M, who the object which is applying the force, small m which is experiencing the force, over r square. Okay, so this is the formula. So when we solve it for small g value is f over m. let's apply this. So capital G m over r square over m. So m and m will get cancelled out. So the small g value you will going to get it as g m over r square. Correct?
Yes, ma'am.
Anything you want to ask?
No, ma'am.
So this is what this is field strength. Okay. Now
Yes, ma'am.
after this we are having field lines. Did you got the notes or not?
Yes, yes, ma'am.
Now you have got the notes, na?
Oh, the notes, ma'am.
Yeah.
No, ma'am. Like I tried to logging in, but I couldn't like press even in my phone
Check
or the
the screen.
laptop.
I'm already shared. I'm sharing it again. Okay. So
Share
copy the link
entire.
of the notebook. Sorry.
Yes, ma'am. You can do that.
Hmm. So I'm entering in your front only. Okay.
Okay. Yes, ma'am.
So I'm just putting your things to can view. Okay.
Yes, ma'am.
Okay. Or otherwise I will say copy. Okay. So this is the link. I'm copying it. Now I'm sending it to Miss Sonia. Okay.
Okay, ma'am.
Okay. I had texted her. Now if she send it to you, then it's good.
Okay, ma'am. I
Okay.
will check
Yeah.
this time.
She will send it to you. Done. Now
Yes,
let's
ma'am.
start doing a next line, and that is field lines. Okay.
Yes,
So the next topic is field lines. So field lines are basically drawn in the direction that a mass would accelerate in. Okay. And if it is
yes,
placed in the field, they will use to help the visualize the field. Okay. Now here the direction of the arrow will give the direction of the field, obviously. Okay.
yes. And
And if it is drawn parallel,
there was one question I saw in the past paper which kind of correlates this and the electricity.
hmm,
Uh, like we kind of use two equations to solve the to find something.
two
I
equations to solve the.
to find the magnetic field, I think.
Uh-huh.
But it was like it was like an entire chapter. It was electricity and it
Hmm.
was from circles.
Okay, so let the electricity chapter come, then we will discuss that,
Okay, ma'am.
isn't it? That would be more convenient. Yeah. So let's come over here. So here it is a uniform field. Parallel line and equidistant line shows the uniform field. Okay, and the direction gives you the direction of the field. Done. When you are doing addition of this, you have to always apply the vector rule, that is tail to head, tail to head. Let's say this is G1, let's say this is G2, then you have to give the resultant G, and your resultant G will be always under root G1 square plus G2 square. Okay. You can apply the thorough formula of the vector addition, that is under root G1 square plus G2 square. Whatever the quantities are, I am talking the angle in between of that. Always. Okay. So it will be 2G1 G2 cos 90, which is nothing but 0. Hence you are remaining with these two, which is given over here. Done.
Yes, ma'am.
So the addition of the field lines or field strength will always be the vector addition. Remember this thing. Okay.
Okay, ma'am.
So suppose one field is given over here, one field is given over here. Now how will you add it? So you can parallelly shift it.
Yes, ma'am.
I bring it here. Now I can bring it here also. But you have to remember that the direction should not change, magnitude should not change. When I bring it here, then resultant will be this is tail to head, then This will be the resultant. Understood how to do?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay, let's do one question then.
Okay, ma'am.
And the question is, here, calculate the gravitational field strength at point A. Okay, so let's calculate it. So this is the larger, we have to find at A. So this is larger mass, this is smaller mass. So field strength due to large mass, and that will be what? Obviously, capital G into 1000 is the mass. Gm over r
Yes,
square
ma'am.
is the formula for
Yes,
field strength. We have sorted just before a few seconds. Okay.
yes,
So
ma'am.
r square is how much from A? It is 2.5. So 2.5 square. Answer where you will get something like 1.07 10 raised to minus 8 Newton per kg. Let's solve for the field strength due to small mass. And that would be how much? Capital G again, and this is 100, this is 2.5 from A, right? So multiply 100 over 2.5 square. This would be 1.07 into 10 raised to minus 9 Newton per kg. Okay.
Yes, ma'am.
So the total field strength will be the vector addition, as I said. So 1.07 10 raised to minus 8 minus 1.07 into 10 raised to minus 9. Check. Anything is wrong? Why I'm putting minus? Because one is coming from this end, one is coming from this end. So they are opposite to each other, the field and the strengths. Okay. So it will
Yes,
be 9.63 into 10 raised to minus 9 Newton per kg. This will be the answer. Okay.
okay, ma'am.
Any doubts?
No, ma'am.
Okay. Let's solve for the next, and that is gravitational potential in a uniform field. So what is the gravitational potential in a uniform field? Let's have a look over this part also. So basically what happens is you will get uh, basically as you lift up mass of m, okay, let's say from the ground, you do some work, okay, and this increases the potential energy as you increase the height, right? Fine.
Yes,
So the potential energy depends upon the mass, okay, and it is also dependent upon the height, right? So
yes,
where you are basically giving a quantity, that is the what is the gravitational potential. So the gravitational potential is a very useful quantity. Why? Because it help us to calculate the how much potential energy per unit mass will be required to place a particular object, right? Now the
yes,
potential is nothing but the potential energy per unit mass, okay? And the for calculation in the uniform field, if we are doing it, is convenient that if we assume that the surface, okay, something like the surface of earth is having zero potential, okay, because already if the surface is also having the potential, then it will also try to attract that object, isn't it?
yes, ma'am.
Okay, so the gravitational potential therefore can be calculated in the uniform field as work done per unit mass, isn't it? So what will be the
Yes,
that we think work done per unit mass? This thing we are already aware, right? Okay, and it is always taken from zero potential to some, let's say I'm writing here infinity, not infinity, but let's say some word a potential. Done. Where a is
yes,
some coefficient. Okay. So in the simple example, let's say of masses which is kept in the room, in which we define that the floor is having zero potential, then the potential is directly proportional to the height when you bring it to the when you bring different masses at a given heights. Okay. So
Yes, ma'am.
here a mass m is placed at some height, let's say in the room. Okay, and we have the potential energy in that. Okay, so by joining all the positions of the same potential, we get a surface of equipotential surface. Okay, let me give you the particular thing about it. Okay, check this question. Okay. So here 0 meters mean the ground surface. We have to potential calculate the potential at A. So as the height is increasing, let's say for C, the potential will be the highest because the potential energy is highest, right? And the potential is defined as what? Work done per unit mass. Okay. Isn't it?
Yes. Yes, ma'am.
Okay. So how will you going to actually calculate it? So we have to calculate the potential at A. So we are aware work done per unit mass is nothing but the increase in the this energy. What should I say? Potential energy, isn't it?
Yes, ma'am.
Okay. And potential is also defined as work done per unit mass.
Yes, ma'am.
Okay. So when I actually define the two, it is nothing but energy per unit mass. Energy is obviously mgh over m. So mm will get cancelled out and I'll be remaining with VA equals to GH. Isn't it?
Yes, ma'am.
It is mgh over m cancelled out. I got gh over m. Isn't it? So what
Yes,
should
ma'am.
be my answer? My answer should be G is given as 10. Height is given as over here. So I think this is 3 meters. So potential
Zero
will be
one.
30 joule per
Yes.
kg. Clear?
Yes, ma'am.
Understood? Okay. Any doubts?
Yes. No, ma'am.
Okay. So now let's discuss about. So basically, if any field is there, we say that throughout the field, your field is uniform in nature. That means at a given altitude, the potential will be same. At a given altitude, the potential will be same. At a given altitude, the potential will be same. At a given altitude, the potential will be same. Understood? This is how we calculate. And we always consider that at ground, the potential will be what? Zero. And gradually it increases as the height increases. Understood?
Yes, ma'am.
Sure?
Yes, ma'am.
Okay. Let's discuss the next pointer, and that is equipotential and field lines. So what do we understand by equipotential and the field lines is, if suppose we draw the field lines in 15-meter of the room, let me give you that room so that you will understand it better. Check this room. Okay. Why do we are doing equipotential surface, Akshita? Because that if suppose I am considering that if I compare it with my earth, okay, then close to that the lines of equipotential surface join points, right? That are the
Yes.
same that are of the same height above the ground. Now these are same as that contours on the map also. Okay. So we also consider that if this is my earth, then from here the line at a given altitude, let's say 100 meters, let's say at 200 meters, let's say at 300 meters from the earth's surface. So here, here, everywhere we consider the potential is equal. Why do we consider that? Because here I am considering the potential is zero everywhere on the surface. Making sense?
Yes, ma'am.
Just 1 second, Akshita. Just Okay. So
Yes,
coming
ma'am.
back to the pointer, I'm saying that if suppose I consider a room in which the 0 meter is representing your ground surface and 15 meter is the height till which we are observing different points are there which are experiencing different gravitational potentials. Done. So here,
Yes,
suppose if I draw the field lines in the 15-meter room, then they will look like something like this, isn't it? And the field is uniform. So they are parallel and equal. That means they are, if I am drawing parallel lines and equidistant from each other, that means they are representing the equipotential surface. Understood?
yes, ma'am.
Okay. Now here the potential energy is increasing as the height is increasing. Okay. Also, if we travel the perpendicular to these field lines, that is from A to E, then there will be no work done. Obviously. Why? Because A to E the height is not changing. So work done will be zero because work done is nothing but F dot ds, and here if I consider it mgh, so no height is changing, hence the work done will be zero, isn't it?
Yes, ma'am.
Okay, so at the same altitude you do no work. Okay.
Yes, ma'am.
Okay, so here uh, for this equipotential surface, let's calculate that how the potential and the field strength is connected. So when we derive that particular formula, we have in our hand that the amount of work done to move up is equal to change in potential. Okay, and also multiplied by mass. Correct? So work done is nothing but change in potential multiply mass. Do you know this why or not?
Mm, because uh, means the change in potential. Uh,
No, Akshita, listen very carefully. Just before a few seconds, I had told you that the potential is nothing but work done per unit mass. Correct? What is
yes,
work done? Work done is nothing but mgh
yes,
over m. So mm will get cancelled out. I am remaining with gh value. Gh value is what? My Vg. So if I multiply my Vg value with m, Vg value with m, I will get mgh. That is the work done. Correct?
yes, ma'am.
Now you understood why it is the value.
Yes, ma'am.
Very good. So now from here, I have, but the work done as you, one second, but the work done, move up is done. Okay, but the work done is also equal to that force into distance is equal to mg delta h, correct?
Yes, ma'am.
So I can write it as Vg multiply m is nothing but mg delta h. So m will get cancelled out and I am remaining with what? The change in potential, let's say. So when I'm changing my potential, I will get change in potential over change in height. That will give me the gravitational strength. So this is the another formula which connects the strength, height and your gravitational, oh sorry, the gravitational potential, strength and the height. Okay.
Yes,
The
ma'am.
first formula we had seen was this. Remember?
Yes, ma'am.
Now this is the second formula. All these formulas are given in your formula booklet. You have to apply this formula as per the demand of the question. Now from here I can conclude that the higher is the sorry, the closer is the gravitational field lines, that is the gravitational potential, okay, the stronger will be the field, isn't it?
Yes, ma'am.
Okay, now let's calculate next thing, and that is gravitational potential due to massive sphere. Okay, so basically let's take it with one example that you will understand much better, I guess. I'm comparing with some mass which is placed at infinity in the space and the earth is trying to attract it. Okay. Can you see here?
Yes, ma'am.
Okay. So basically, hmm. So here the work done per unit mass, taking the mass from a position, let's say from infinity to a given point, let's say P, is defined as the gravitational potential. Okay. I'm saying gravitational potential at point P is defined as work done per unit mass in bringing mass m from position infinity or 0 to a given point P. Understood? This is the definition. Shall I write it?
Yes, ma'am.
Okay. Wherever potential is coming, no, you have to define it in the same way. Amount of work done to bring this particular thing from given point to the another given point. It is always like that. In
Yes.
electric field also it is like same. Okay.
Yes, ma'am.
Done. So here the earth surface is representing the zero potential, but somewhere where the mass m is not affected at all, no, somewhere the mass m which is not experiencing any potential, that is said to be infinity. Okay.
Yes, ma'am.
At infinity we always consider the potential is zero.
Yes, ma'am.
Okay. So the potential is defined as work done per unit mass. Okay. So what work you are doing when you are bringing it from infinity to a given point? Obviously no work because it is infinity and here the potential is zero. So you are doing no work in against of it. So let's consider this one that I am bringing from P point because at P point potential is experienced by earth, isn't it? So
Yes,
let's
ma'am.
do that. I am bringing the mass from here to here. Why I am saying this? Because if I calculate this one, I can apply it over this one as the force and the field is totally conservative in nature. Here the energy is totally conservative in nature, isn't it? It is a cyclic process. The work done to bring it from here to here and the work done from here to here will be zero because one is in the plus direction, one is in the minus direction. It is a cyclic process. So the total work done will be zero, isn't it?
Yes, ma'am.
Okay. Due to conservation of energy law, due to conservation of momentum law. Anything you want to ask?
No, ma'am.
Okay. So if I say that I have brought the mass from point P to point infinity, then I will calculate that and after that I can put a minus. So my formula will be this, isn't it?
Yes, ma'am.
Okay. Now you understood now why did I put minus? So
Yes,
let's
ma'am.
calculate this point. So my VG is nothing but work done per unit mass. Now work done is nothing but F dot delta S over M, isn't it? So what is F? F is nothing but we had calculated GMM over R square. Delta S is obviously R only. See, R is the distance at potential P. So as I'm going away, R will going to increase, isn't it? So R
Yes, ma'am.
square delta S is how much? R. Correct?
Yes, ma'am.
Okay. Anything you want to ask?
No, ma'am.
Okay. So it is divided over M. M and M got cancelled. R and R got cancelled.
Yes, ma'am.
So the value of VG will be GM over R.
Ah.
Any doubts?
No, ma'am.
Sure.
Yes, ma'am.
Where small g is defined as VG over delta X. Okay.
Yes, ma'am.
Okay. Now let's see equipotential surfaces after this. Now, how does the equipotential surface look like? Let's have a look over that. one more thing, Akshita, that I need to explain you, that for this part only,
Yes, ma'am.
and that is this graph. The force against the distance of the test mass when it moved towards M, capital M. Where is the capital M? This one is the capital M. Okay, how much is the force applied? So the force against of the distance gradually increases as the distance is increasing. Why? Because, sorry, force is decreasing. My bad. Force is decreasing, isn't it?
Yes, ma'am.
Hmm. As the distance is increasing. Okay.
Yes, ma'am. Yes, ma'am.
Any doubts?
No, ma'am.
This though we are already aware with the formula also, but still the graph matters us a lot. It may come in your exam. That's why I'm explaining this. Okay. I hope you are having no doubt in this.
Yes, ma'am.
Okay. So now after this, we are having this formula also, and that is potential against the distance, as the potential is also directly proportional to forward force over mass, isn't it?
Yes, ma'am.
Potential is what? Force over mass, isn't it?
Yes, ma'am.
Okay. So force is obviously, I had told you it decreases as the r decreases. Hence, the potential will also decrease as the distance increase. Okay. So the
Yes.
potential decreases as the distance increases. Any doubt?
No, ma'am.
Okay. Now let's have a look at the equipotential surface also. These graph actually may come in exam, so I had shown you.
Okay.
And they are always drawn in the negative terminology. But I told you why. Because rather than counting from infinity to p point, we always count pre to infinity and then we put a minus over it.
Yes, ma'am.
Any doubts?
No, ma'am. On yeah, just give me a
That's why the
second.
graph is negative.
Okay,
Yeah,
ma'am.
please do.
Yes, ma'am.
Okay, check. So these are the equipotential surfaces. Field lines are broadly increasing concentric circle. Why I am showing you this? It's very important. This diagram always comes in exam to draw. Draw the equipotential surface. So as you go away from the point, the distance increases.
Yes, ma'am.
Okay,
Yes.
gradually. This shows that the field is decreasing. Field strength is decreasing.
Yes, ma'am.
Okay, any doubts that you have over
No,
here?
no, ma'am.
Sure. Now after this, we are having that what will be the addition of the potential at a given point. Okay, let's discuss that part also. So how does the potential gets added? It's simply added like a scalar quantity. Okay, do you know what is a scalar quantity?
It only has
Yeah,
direct.
only magnitude. You have to do plus and minus in that as per the given directions. Okay, so check.
Yes, ma'am.
So at P point, if I am considering for MA mass, it will be this much. If I
Yes.
consider from MB mass, it will be this much. So the total potential will be just added, nothing else.
Okay, ma'am.
Okay, anything you want to ask?
No, ma'am.
Sure.
Yes, ma'am.
Always capital M is who is applying the force, small m who is receiving the force. Okay.
Yes, ma'am.
Okay, now after this, we are having our next topic, and that is escape velocity. So basically, the escaping velocity from Earth's surface is 11.2 kilometer per second. If you are having this much of the speed, ideally, you can escape from the Earth's gravitational pull. Now let's have a look that how it has been derived. So for that, we have a diagram which is given as like this. Check. Okay. So here a mass M is thrown away from the earth. RE is when it is going near to the surface of earth. R2 is when it is going away from the surface of earth. Okay. Now I am deriving it when it had gone away. Okay. The same diagram I am explaining over here. Just check. Okay. So basically the potential energy, okay, or I should say that if suppose a body is thrown, okay, that is straight up from the surface of earth, then the kinetic energy decreases as it rises from the surface of earth. Okay. And hence we ignore the air resistance over here so that we can calculate the standard and the ideal cases. Done. Now the energy is transferred to the potential energy, isn't it? As the height is increasing, potential energy will increase.
Yes, ma'am.
Okay. So that means what? My half mv square is converting into mgh, isn't it?
Yes, ma'am.
Okay. So if we throw the body up, it really becomes very fast because it might get so high that the gravitational field strength would start to meaningfully decrease, isn't it? And in that case, we will use the formula that the potential energy is given by this. Check. How do we derive potential energy? So the potential energy is nothing but mgh. Mgh is nothing but work done, and that is nothing but F dot delta S. That is nothing but what? I had given you the formula gmm over r square. Delta S is r, so r and r will get cancelled out. So the potential energy formula is gmm over r. Making sense?
Yes, ma'am.
Anything you want to ask?
No, ma'am.
Okay, so from this formula I had derived this one. At point P. Okay. So basically just near to the surface of earth and when it goes away. So as it has reached the potential energy, okay, for this given mass, this is the unit test mass. Okay. When it is going away from us, it's shown by like this. And the loss of kinetic energy is given by the gain in potential energy. So as it is going away from us in the initial stage, the speed was 0 for the ball. Then it started to move. So half mv square minus 0. Making sense or not?
Yes,
Anything
ma'am.
you want to ask?
No, ma'am.
Sure.
Yes, ma'am.
Okay, great. So now after this, we are having that rearranging these formula. Okay, GH. In MGH, obviously we will change the height. So height 2 minus height 1 I am doing. This is height 2, that is at R2 distance. Height 1, this is at RE distance. So I had given this. Check. Any doubts if you are having? Final point minus initial point. This is what has been done in MGH. That is the potential energy.
Yes, ma'am.
Are you sure that you are having no doubt?
No, ma'am.
Okay. Why did I set this formula? Because we are derived with this.
Yes,
Okay.
ma'am.
Anything you want to ask?
No, ma'am. I'm writing down in the
Oh, yeah, sure. Please write it.
class. Can you scroll down a bit, ma'am?
Yeah, sure.
The work done. Yes, ma'am. Yes,
Done?
yes,
Okay. So after, if we throw the ball very fast enough that it will never come back, this means that it had reached at a place where it had gone under the no longer attracted by the earth, and we call that point as infinity, because we always say that infinity, the potential is always how much? Zero. Okay.
yes, ma'am.
Done. So of course it actually reach infinity, but substituting r to infinity, obviously I had told you that if I put infinity in the 1 over infinity is 0, isn't it?
Yes, ma'am.
So this thing will become 0. So I'm remaining with half mv square in this formula. Correct?
Yes,
Anything
ma'am.
you want to ask? Done.
No, ma'am.
Now, so out of here, can found the escape velocity v keeping here, and I have found out this much. So when it is calculated, it is this much. Okay. Any
Yes.
doubts?
No, ma'am.
Sure.
Yes, ma'am.
Okay. Now, question is why the Earth has an atmosphere but the Moon does not has. I'm explaining you the reasoning also simultaneously.
Okay.
Okay. Because these questions come in exam. Okay, why the Earth has an atmosphere but the Moon does not. So basically, the average velocity of the air molecule at the surface of Earth is 500 meter per second. Okay, which is very much less than the velocity required to escape the Earth, which is nothing but 11 kilometer per second. Check.
Yes, ma'am.
Okay. So, however, 500 meter per second is the average velocity or the average speed. A lot of molecules would also be traveling faster than this also. Okay. So, they lead to a significant number of escaping. Okay. So, they would escape the earth, whereas many of them does not escape. Okay. Now, factor is, let's compare it with the moon also. So, there the escape velocity for the moon is 2.4, and obviously the molecules are moving with this much of the velocity, which is very much greater than the escape velocity of the moon. This is for earth, and that is 2.4 kilometer per second. Why? Because 1/6, what is happening? Yeah, the g of earth is 1/6 of g of moon. Okay.
Yes, ma'am.
I had written vice versa, I guess. The 1/6 of g of earth will be the g of moon. That means the mass of moon is 6 times smaller in comparison to earth. Hence the escape velocity over moon is quite small. You can see over here. Okay. Hence it escapes out. Anything you want to ask? Now it's quite logical. After this, you do not need any other option to say that why atmosphere is there good on the earth but not on the moon. Correct?
Yes, ma'am.
Okay. Anything you want to ask out of it?
No, ma'am.
Okay. Now let's talk about black holes also. Okay. So basically, a star is a big ball of gas, okay, which is held together by the gravitational force. And this is the reason of the force that does not cause the star to collapse. Done?
Yes, ma'am.
Because the particles are continuously giving the kinetic energy from the nuclear reaction, okay. And as the time progresses, the nuclear fuel gets used up. So the star does not collapse.
Yes, ma'am.
Okay. Now, as this happens, the escape velocity also increases until it is greater than the speed of the light.
Yes, ma'am.
Okay. So, at this point, not even the light can escape, and the star has formed like a black hole. Understood?
Yes, ma'am.
Okay. Anything you want to ask?
No, ma'am.
Sure?
Yes, ma'am.
Okay. So, now after this, we have the solar system. So, solar system obviously is shown something like okay, so it is shown something like this. If suppose this is my sun, this is the orbit, here is the earth, then it is moving along the radius towards the center. The force is gmm over r square. Correct?
Yes, ma'am.
Anything you want to ask?
No, ma'am.
Okay. So the force, gravitational force is acting as the centripetal force. GMM over R square is the formula for this. Okay. So here basically they are moving in an angular motion, in an orbital motion. Hence my M omega square R is given as GMM over R square. M omega R square is torque. Remember or not? Shall I explain this?
Yes, ma'am. No, ma'am. No, ma'am.
Yeah, centripetal force.
Yeah, 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 yeah.
Okay.
Yes, ma'am.
Centripetal force was mv square over r. V equals to omega r. You apply this over here, you will get this much. Okay,
Yes, ma'am.
done. Now omega is also equals to 2 pi over t. So when I apply this over in the above equation, I will get m 2 pi over t whole square r equals to gmm over r square. So when I compare all those things, I will be getting t square over r cube equals to 4 pi square over gm. Okay, so this is basically the Kepler's third law.
Yes, ma'am.
Okay, that the square of the time elapsed by the particular planet around the star is inversely proportional to the cube root of the distance of the planet from the earth. Okay.
Yes, ma'am.
Okay, so fine, this is it for the day. Okay, we will
Okay.
we will continue it tomorrow. Done.
Yes, ma'am.
Okay, fine. So bye Akshita, have a nice day.